Thanks for the invitation. And
I've come a long way.
yeah, this is first time for me. So this is about the conjecture by Lovaas and Plummer in 1970s. So let me first begin with a few terms. So let me first say what a perfect matching means. So many of you know already this. So perfect matching is a set of edges such that no two edges share a vertex, and every vertex is covered by some edge. Right? So it's a set of edges. So no two share a vertex, and it covers so that's perfect matching. Some people call it a one factor. It's the same terminology. So one factor means a spanning, it's a subgraph in which every vertex has degree 1. Right? So in a sense, if you have perfect matching in a graph, then in this graph, every vertex has exactly one incident edge, so we call it a one vector.
So spanning subgraph.
Yeah, spanning subgraph. So spanning one regular subgraph. Also, you can define K factor as well. That's a spanning K regular subgraph. Right? So it's generalization, right? So you increase 1 to 2, 3, 4. Right? And let me say a few words about cut edge. So an edge is cut edge if it looks like this. So if it looks like this, where if you delete an edge, the graph has more components. Right? So the number of components, so G delete has more components. If this happens, then we call this a cut edge. And then you might wonder when a graph has a perfect matching or not. And that's a useful question to know, because in many cases we want to find, we want to solve marriage problems. Here everybody is male, so nothing to make up. But in general, there is a theorem by Peterson in 1891, and saying that every cubic graph, so cubic means is 3 regular. So every vertex has exactly 3 instant edges. Yeah. So every cubic graph with no cut edge has a perfect match. So that's an old theorem, and for those who took the graph theory course, this is one of the corollaries of the touch theorem. Right? So it's well known, and it's necessary to have this condition. If you have a cut edge, you might have no perfect matchings. And for instance, I might have a graph that looks like this. So this is an example of graph. So it's a cubic because every vertex has exactly 3 instant edges. Right? And yet, it doesn't have a perfect matching. If it does, then this vertex has to find his partner. But it's symmetric, so we can assume that maybe this edge is chosen. But we have then problem here. You have only 1, 2, 3, 4, 5. You have 5 vertices there, but you need to have even number of vertices, so it's impossible. So you can never have a perfect matching in this graph. So it is necessary to have no cut edges. And then what Roberts and Plummer conjectured is the following. So that's in the 70s, and saying that, I mean, in this Peterson's theorem, they only guarantee that there is at least one perfect matching. Okay? So you can say this as at least one perfect matching. But how many are there? And they conjecture that it's at least 2 to the c times n perfect matchings for some constant c. Okay? So what they want to know is that actually there are a lot of perfect matchings, not just one.
In a cubic.
Yeah, in a cubic
Graph with n vertices.
graph with n vertices without cut edges. Okay? So n is the number of vertices. Okay? So we should have the same condition. So the graph is cubic, so every vertex has 3 incident edges. It shouldn't have any cut edge. And that's the conjecture. I'm not saying that I solved it. I'm saying I have an additional condition. So if I restrict the problem to subclass, then that's what I'm saying. All right, so let me first survey what's known. So this is known to be true for small number of cases. So it's true for bipartite. So if you can partition the graph into 2 sets so that all the edges are between this set to the other set. Okay? So, or if you don't have any cycle of odd lengths, then the conjecture is true, and the number you get is something like, so their bound is 6 times 4 over 3 to the n over 2 minus 3. So that's the bound known. So it's, oops. That's 79. So what am I saying?
So what is the special meaning of c? You made 2 to the c, and you can write as c to the n, where c is
That's right. Yeah, the same.
Bigger than 1.
Yeah, I just like 2, so yeah.
You can write p also instead.
I just won't have any exponential function. Alright? So should be alright. Okay? What they are saying is there are exponentially many perfect matchings.
Okay.
So yeah, in this way we can write 2 to the n times log of something, right? So anyway. So for bipartite graph, it was known long before, right? So it's in 79, and the proof is not that long. It's short. And it's known for planar graphs. And this is sort of surprising. So I learned this conjecture by Chudnovsky and Paul Seymour last year. So this was the result last year, and their bound is on 2 to the n over 655978752. So that's what they have. So, and they indeed need that number. So they decompose the graph and they came up with the best bound that they can get, and that was the best number that they can get. Right? So they proved what? Every cubic planar graph with no cut edge has at least that many perfect matchings. And their tree cannot be generalized to general graph because they use four-color theorem. So the four-color theorem can be only used for planar graphs. So any planar graph can be colored with four colors. If you go to dual, then any cubic planar graph with no cut edge can be partitioned into three perfect matchings, not just one, but three. So four-color theorem gives you, instead of one perfect matching, it gives you three perfect matchings. And then once you have two perfect matchings, you can do lots of tricks. And also there's another point. So they use four-color theorem in two ways, and both of them are difficult to be generalized for general graphs. So these are the only, so far these are the only cases known, right? What about general graphs? So for general graphs, well, instead of exponential function, we might hope for polynomial or some constant or whatever, right? And there was a result by Jack Edmonds, Lovas, and Purlibank in 80s saying, and the consequence of their result will say that there will be at least n over 4 plus 2 perfect matchings. So this is implied by Edmonds, Lovas, and Purlibank. Purlibank. That was 82. So they.
When you say general, how general is it?
Well, I didn't define. So let's not restrict to the bipartite or planar. So just any cubic graph, yeah, for any. Right. So. Right. Not very good. Right. If we don't restrict further, then right. So if it is cubic with no cut edge, then they have a result saying that the polytope made by the perfect matchings of a graph has a certain dimension. And once you have a dimension, then that gives you a lower bound, the number of vertices on the polytope. So that's somehow easy consequence of Deep's theorem. But then nobody looked up until recently. So the Dan Krall and then his friend, maybe Sereni. So they so this was 2008, and they improved it to n over 4 by looking at the polytope and how to make more perfect matchings. But then Krall works on further, so they improved it to 3/4 times n minus 10. So this is again some other people, and then Daniel Krall, same, and then one of his students and another Czech guy. And later this year they proved that it's actually bigger than any constant, any linear function. Well, what that means is if n is large enough. So for any c, I can give you some n such that for any cubic graph with no cut edge, we have at least c times n perfect matchings. So this is again by same set of people. Well, not same, but same E, Spellet and Kardosh and Krar. So that's best thing known so far. So the best known is it's not linear. It's growing faster than any linear function. But it's not known how we can get a exponential bound in general.
Is that constructive? So if I'm giving you a C, then do they know for what n?
Yeah, I think it should be, because all of these depends on, so all of these, so I think this uses induction. So basically you prove you have many perfect matchings here, many perfect matchings there, and yeah, so yeah, it's not like a huge number. There will be something. Right, so that's a current status, and what I want to show is the following. So graph is, if graph is Claude-free, what I mean is it doesn't have this subgraph, this induced subgraph. Okay, so if you have a vertex, then you must have 3 neighbors, and at least one of them, one pair of them, must be adjacent. That's Claude-free. So if I require that condition, then the conjecture is true. So the theorem is if G is cubic Claude-free with more than with no cut edge, then there are many perfect matchings, and we can get it's at least 2 to the n over 18. So it's not that bad. Right. So it's much nicer than this number, and also the proof is much shorter. So their proof goes over, I think, more than 15 or 20 pages. It's complicated, but this one maybe 1 page once you set up everything. So initially I was thinking that problem because recently Chudnovsky and Simmer came up with the structure theorem for describing all Claude-free graphs. So there is a big theorem saying that every Claude-free graph can be built from certain structure like line graph or something else, and then you can glue them together to construct any, no, not quite correct, but in general the principle is you can decompose Claude-free graph into well-known structures. So I was initially what I was thinking is perhaps if since you know structure about Claude-free graphs, there could be a easy way to attack this conjecture for Claude-free graphs. That was my initial impression. But then it turns out that it's much easier than I thought. So that's what I'm going to talk about. Any questions? Do you have any questions?
How many clues are there? I want to see the exact definition of clue. So in that graph.
Oh, in this graph. Yeah, this is one claw, right?
Yeah.
Oh yeah, there are many claws. This is one claw. So, yeah, these are called claw, right? Claw is K13. So there was a reason. Yeah, you need to draw this way.
It should be induced subgraph.
Yeah, it should be induced subgraph, so you shouldn't have any edges between them. And another reason why I was thinking about Claude-free graphs was because there is a theorem by somewhere. So another theorem, this was in 70s, saying that every curve-free graph, so let's say connected with even number of vertices has a perfect matching. So that's another theorem on perfect matchings. So any curve-free graph, as long as you have an obvious condition that the component must have even number of vertices, then it has a perfect matching. So if you look at that, maybe you might argue, oh, so it must be easy to construct perfect matchings because that theorem may give you some hint. So both of them are used as a exercise in graph theory course. So you might remember. All right, so that's
Also, graph has
Yeah.
K close.
yeah.
Can you use that information to improve this theorem?
Right. So I was thinking about that with Jung-Jisoo. So yeah, I will talk about that later. So if you have only small number of close, then yeah. So originally the story is this. So he is undergraduate student sitting there. And he wanted to do some undergraduate research, independent research in the summer. So I wanted to give him a problem. So I gave him this problem, just this problem. But next week I solved it. So then what should I do? Then I realized maybe I should give a different problem. So then I give your problem. So restrict the number of claws and then solve the same conjecture. But anyway, that's what I would like to give a talk today. So I will show you the proof if you don't ask more questions. Any other questions? So the proof consists of two parts. So basically, I need to understand how the graph looks like. Yeah, so proof will be basically in two parts. I need a structure, and then once we understand the structure, then we can talk about two big cases to consider. So either if this happens, then you have a good property. If this doesn't happen, you still have a good property. So that's our ingredient. So let me first describe the structure. So if graph is curve-free, then every vertex, each observation is this. Every vertex is in 1, 2, or 3 triangles. Yeah, it's curve-free, so, and it's cubic, so you have a degree 3. So at least one pair should be adjacent. Yeah, so either you have one edge here, or 2 edges there, or 3 edges, right? So depending on how many edges you have in the neighbors. So that's obvious. So let's say you have a vertex in the
This is the case with 3 triangles.
Yeah, this is the case where you have 3 triangles.
It's the only case.
Yeah.
Okay.
So that case is done. Yeah? You have one single graph. As long as you assume the graph is connected. Yeah, I can assume the graph is connected because otherwise I have 2 components maybe. If it's not connected, then what? You have a 2 to the n1 over 18 times 2 to the n2 over 18, and then you can add them, right? So you can add these together, right? So if you have if you can decompose graph into 2 pieces with n1 vertices and 2 vertices, you can just apply induction. So you can assume the graph is connected. Then as soon as you have a vertex in 3 triangles, then the graph itself is K4. So you have nothing to do. So now we can assume that no vertex is in 3 triangles. So let's look at the case when you have a vertex in 2 triangles. Then you might as well draw a graph like this. And then this will be also in 2 triangles. And these guys will not be adjacent. So it must look like this. Right? So I call it a diamond. Right? So we call this diamond. And then this will be in 1 triangle, 1 triangle. And then if I remove all the diamonds, then so these 4 vertices form a diamond. Then all other vertices will be something like this, right? Right? So this is in 1 triangle. This vertex is in 1 triangle. This vertex is in 1 triangle. So other than diamonds, everybody looks like this. So I call it a triangle. Obvious name.
What do you mean remove?
I mean, I'm not removing, but other than these vertices, all the remaining vertices will be in this configuration. So you can find the triple of vertices in the same triangle. So this will be called the triangle.
But you have only one edge going out from everywhere, right?
Yeah, because it's a degree 3. Yeah.
So then you should write just 1, not 2.
Yeah, this is number 1.
Ah.
Okay, so number 1. All right? So I will show you how I can reduce diamonds. So the name is not very exciting. You don't want to remove diamond in general. So what I want to do is replace this diamond by single edge. So if I have something like this, replace this by an edge. And I conjecture, no, I think I claim that so if this was G, if this is H, if G, then H is claw-free. And H has no parallel edges. And it has no cut edges. So far, the conjecture is about the simple graphs. Yeah, you don't have loops, you don't have parallel edges. So by reducing the diamonds to an edge, I don't want to introduce parallel edges. And yet, I still want to make sure that H is cubic. Yeah, claw-free cubic. So many things should be obvious. So it should be claw-free. So suppose not. I replace diamonds by an edge. If you got a claw, then the only way you can make claw is to have something like this. Right? But then initially you have this drawing. Right? So you glue these 3 things, you got a claw in G. So H is claw-free. It's cubic, obviously. You just remove these guys, connect those 2 vertices, so it's cubic. Every vertex still has the same number of edges. It doesn't have parallel edges. Then you need a check. So how can make a parallel edges. The only way you can make it is you replace this, but you might have this single edge gluing these two vertices. Then you might create a parallel edges. So let's see what happens here. Then this guy has degree 2 now, so I need to have another edge. So going out. Then if you look at this and that edge and this edge, that's close. It cannot be close, but this vertex has degree 3 already. So the only way to make sure that you have no close is to have this edge. Right? And then this vertex has degree 2, so you have some edge like this. And then all other vertices here have degree 3. And then this is cut edge. In G. Well, initially we said our graph has no cut edge, so that's not possible. So you don't create parallel edges. No cut edge is easy because you have a side. The graph was two edge connected initially, so replacing this would not create a cut edge. Yeah. So if this was cut edge, then this will be cut edge as well, but that's not true. Right, so we can remove diamond while maintaining the same property. So let's try to remove as far as we can. So imagine that you removed all the diamonds. Where one case may be a travel, the graph may have no triangles. Yeah, you might have no triangle in this case. So we call it a ring of diamonds. Yeah, so if this is the case, you have nothing to do. But anyway, you know there are lots of perfect matchings. So you win again. You have many perfect matchings anyway, so you can assume that there are triangles. So by this lemma, we reduce all the diamonds, then your graph may look like this. Right? You have many triangles.
Will you discuss what happens for the number of matchings under installing this and deleting this?
Yeah, I didn't yet say anything about number of matchings. Yeah, it's gonna reduce. It's gonna be reduced, right?
I mean, you must prove that when you remove a diamond, that this removes by a certain factor, right, which is positive or whatever. But
Yeah, if it's a factor, then there will be a fantastic.
2 to the 4, 2 to the 2 over 9 or something or whatever.
So I cannot say that it's gonna reduce the perfect matchings by some factor.
But then
So-
you want to prove that.
Yeah, so we'll see. It's not induction, actually. My proof is not based on induction. Only this part is about induction, but
Okay.
once you assume it's connected, then it's algebraic proof. So we know the structure. Yeah, so the graph may look like this. You have a bunch of triangles, and then between triangles, you have edges. And this is curve-free automatically. Any graph you can obtain by this construction is curve-free because every vertex is in one triangle. So you can construct all, and this is easy to see. And then let's say,
So you mean you take a cubic graph and then you blow up every vertex by a triangle.
yeah,
But you might have also a multiple edge in this case, right?
right, yeah. So initially I might have a multiple edge. I blow up, then I can get any graph like this. But I usually say it the other way around. So I got this graph, contract every triangle into single vertex. What we get is a cubic multigraph. You may have a parallel edges. Cubic multigraph without loops. Okay, so let's say T is the number of triangles. Right? So after removing all the diamonds, you might have many triangles. And if this has many perfect, okay, so let me say a few words. So initially I want to prove that there are many perfect matchings, but perfect matchings are one factors. If you take a complement of perfect matching, then every vertex has two edges. So that's two factor. So instead of perfect matching, we can talk about two factors. Just by taking complement, it's cubic graph. Right? So two factor in cubic graph looks like unions of cycles. Right? The goal is to show, I want to show that there are many two factors. Right? So once we have structure, now we are using the structure to prove that there are many two factors. But three regular graph, two factors looks strange. So two factor is going to be just a disjoint union of cycles. Right? So if you have you might something like this, right? So for every vertex, you have to take two edges and select it. So one of the way you can make a one two factor obviously is to take each triangle once. Right? That's two factor. But let's say this is graph G, and let H be a G, and you contract all triangles. So from this graph, let's contract every triangle to single vertex. So you have 1, 2, 3, 4 vertices, and these are adjacent. So this is the new graph H. From this two factor, I have nothing, right? But depending on two factor, I will have something. So some two factors may use edges like coming in and go around. This may be one of the two factor, right? If you contract all the triangles, when you get is this cycle, right? And
plus 1 point. Plus 1 point. The other vertex. And this one, yeah.
Yeah. Once you contract it, you have nothing. That's right. So, yeah.
No point.
That depends on the definition of cycle, right? So,
I'm a topologist.
okay. All right. Okay. So what I'm saying is that if you have a cycle of H, suppose you have a cycle in graph H. What you can do here is to just take the edges in the cycle. So you have a cycle here, and take edges in the cycle, and then route through triangle properly to consume all vertices in the triangle. And for the remaining triangle, you can just route like this. So for every cycle of H, you can get a two factor of G quite easily. And that's one-to-one mapping, right? So if you have a different cycle, you get different two vector.
But you mean it can be a union of cycles.
Right, so I was going to say that, right? So if you have a sum,
Disjoint, they should be
symmetric sum or whatever. So cycles member of a cycle space. So cycle space is a vector space which is spanned by all cycles of graph, and the sum is the GF2 sum. So if two edges are, if you have a cycle like this, cycle like that, C1, C2, then C1 plus C2 is this. Then you can think about vector space spanned by all cycles of the graph. So
means that two vector space or what?
yeah. So over this field. So let's write this way: C of H. As long as you have a member, then any cycle in any cycle space, every vertex has even degree. Also, in any member of cycle space, since you add these guys, so every vertex has even degree in the right. So you add the right. So this guy, this yes. Okay. Let me write. If X is in the C of H, then each vertex means even number of edges in X. And that's why actually that's if and only if. Right? So in other words, it's a set of Eulerian subgraphs. So as long as you have a member of cycle space, but in a cubic graph, even means 0 or 2. Right? So either you don't use a vertex or you use a vertex with twice. So any member of cycle space is going to be disjoint union, vertex disjoint union of cycles. Right? So you have a vertex disjoint union of cycles. For each of them, you can draw two vectors, and they are all distinct. So you can get two vectors, and they are equivalent. Right? So you have a mapping from here to there, and you have a mapping from here to there. So what am I saying? So it's enough to argue about the number of vectors in a cycle space, and dimension of the cycle space is what? There's a well-known theorem about this. It's spanned by the number. So if you have a spanning tree, then the cycle space is spanned by the fundamental cycles. So it's a cycle. So for every edge not in this spanning tree, you have one cycle, and these form a basis of the cycle space. So the number of edges not in the spanning tree will be the dimension. So the number of edges is 3/2 times t, because t is the number of triangles, minus what? So number of edges not in the spanning tree. So number of edges in the spanning tree is number of vertices minus 1, so it's t minus 1. So it's t/2 plus 1. So if the dimension is this, then it's a vector space over the binary field. So the number of vectors there is 2 to the t/2 plus 1. So as long as t is big enough, we can argue that there are many two vectors. Yeah. If t is big enough. Is everything clear? Yeah. If t is big, then we are done. Yeah. If you have many triangles, you are done. So the other case is if you have many diamonds. So what if you have many diamonds? right? So you have many diamonds. So when you reduce to this graph, you might have this as, in fact, this was many diamonds, right? Then you route a 2-factor into each diamond in this way. Right? But in that case, if you have a member of cycle space which uses many diamonds, like this, so this edge uses a lot of diamonds, 2 diamonds, then for each diamond you have 2 ways to route it. 2, 2. Right? So if in this case you have 3 diamonds, that means you have at least 2 to the 3 2-factors. So if there are many diamonds, then we want to find the member of cycle space that contains many diamonds, right? The question is, find the member of C of H using many diamonds. Right? Many means linearly many in terms of n. And there, for that, I use the theorem by JJ. So he proved the Novel zero A-flow theorem, saying that every graph with no cut edge has a Novel zero A-flow. That is, you just run the flow on the graph where every edge must have numbers from 1 to 7. And at each vertex, the amount of incoming should be equal to the amount of outgoing. But that's same as Novel zero G2 times G2 times G2 flow. There's a theorem about this. So he proved that every graph with no cut edge has this kind of flow. But that's equivalent to saying that there is 3 members, so C1, C2, C3, members of cycle space, such that the union of the edges is everything. Yeah, so that's equivalent statement. So you have 3 members of cycle space so that they cover the whole graph. So now we are almost done. So for each edge, we just remember how many diamonds you had. Then one of the 3 cycles must contain at least 1/3 of them. So the number of diamonds is n minus 3t over 4. That's the number of diamonds. Okay. And there is a cycle number of cycle space containing 1/3 of them. And then that means there is a cycle using that many diamonds. And then for each diamond you have 2 ways. So it's this. Right? So you have at least that many perfect matchings. So either you have this or that. Okay? So just make sure that you get the same numbers. n minus 3t over 12 is equal. Let's solve this simple equation. And t is 9 of n over 9. Right? So let's put t to be n over 9, then, no, what I mean is, so if t is n over 9, if t is greater than or equal to n over 9, then we use that inequality to say that there are perfect matchings and perfect number of perfect matching is at least n over 18 plus 1. If t is less than n over 9, then we prove because of this, it's greater same. So actually I can remove the equality. So in both cases you win, right? So either you have many triangles, you win, or you have a small number of triangles, you win. So that's it. So let me come back to the question by Dong-Soo Kim. So I asked to Jung Ji-soo about this problem. So let's assume for further generalization that let's say the number of claws is small. Can you prove that the number of perfect matching is small? Oh, no, large. And so we proved something like this. So if G has no diamond, and number of claws is less than n over something. I tried to calculate this number many times, and at each time the number is different. You say it's 11?
No, maybe it's 10.
10? So before I come here, I tried to calculate it, and my number was a bit different. I got something like 11, but then so it's like maybe something plus epsilon or something, and then you have a perfect matching like something like 2 to the epsilon n something. So you choose your favorite epsilon, it's positive. Then as long as you have maybe minus epsilon. So this is the case when you have no diamond. So we want to extend it to the case where you have many diamonds. But then the trouble is to find the appropriate version of Norwegian-Aplow theorem or something like that. I mean, the existence of some members of cycle space using many diamonds, but without using any clause. That was difficult, so we haven't solved it, but so that's it.
So, any questions?
Yep.
So I think maybe you can try to improve a bit the first case by, I mean, when you have one edge that so basically you are looking, so when you have one cycle that has many diamonds, you should have more, but you don't know how to construct them.
Right, so it depends.
So it's not so easy.
Yeah, it's not so easy. It's not like if every member of cycle space uses certain number of diamonds, then we can multiply that, right? But only some cycle uses many diamonds, some cycle uses only small number of diamonds, then you cannot simply multiply, right? So it's additive, but
so you cannot estimate the number of cycles that use many diamonds.
Right, that's something we don't know.
Anyone else? So this claw-free, it's some forbidden induced subgraph.
Yeah, yeah.
Correct? So are there other subgraphs that you can? Is it only claw-free you know so much about that you can make this, or is there some
Maybe
other?
there could be others, yeah. So people are interested in perfect graphs, so they study odd-hole free graphs, or I mean, you can think of any graph you want to do and just do the similar thing.
And is it difficult to explain this? You mentioned something between a perfect matching of a graph and a polytope. Is that
So
difficult to explain? Or?
So if you have m edges, you can think about m-dimensional vector space in the real field. And then if you have a perfect matching using a certain number of edges, then you can think of a characteristic vector. So consider the space, the polytope, made by all those points, made of perfect matchings. And you can think about the dimension. That's what I know. Yeah. And then they know the dimension of the polytope. And they also have a description how you get a polytope by linear programming.
So thank the speaker.
Thank you.